We want to graph f of x equals log base 3 of x and g of x equals log base 1/3 of x, and compare and contrast the two graphs. So when you're presented with a logarithmic function that you want to graph, it's usually easiest to change it out of its log form and rewrite it in its exponential form. So instead of f of x equals log base 3 of x, let me first of all just replace f of x with y. So we have y equals log base 3 of x. And now writing this in its exponential form, we'll have 3 raised to the y power is equal to x. Remember, always starting with the base. 3 raised to the y power equals x. And this is usually an easier form to deal with. If we're looking to generate the graph by making a table of values, it's usually easier to generate the graph from the form 3 to the y is equal to x. Now notice where x and y are. Because y is in the exponent, it would make sense to go ahead and fill the y side of our table with values from -2 to 2, because it's going to be easier for us to input an exponent and then get the output. So if we input an exponent of -2, in other words, we're computing 3 to the -2 power, we know that's 1 over 3 squared, or in other words, that would be 1/9. My x value would be 1/9. So now 3 to the -1 power, 3 to the -1 will be 1 over 3, or 1/3. 3 to the 0 power is 1, 3 to the first is 3, and 3 squared is 9. So these are going to be the values that we will plot in order to graph the function f of x equals log base 3 of x. So we'll continue by plotting these points. When x is 1/9, y is -2, so we're going just barely to the right of the origin, right 1/9 and down 2. You'll probably have a hard time even seeing that point, since the x value is so small, close to 0. And then right 1/3 and down 1, another value that's fractional, close to the y-axis. And then we have our common point 1, 0, so that's going to be our x-intercept. And then right 3 and up 1, and right 9 and up 2. So really it's these 3 points that I've marked in orange. These are our lattice points, or they're the ordered pairs that have integer values that are most important. But the fractional values of x equals 1/9 and x equals 1/3, they are helpful because they do tell us that the behavior of this graph is that it's going down and getting very, very close to that y-axis. It's hugging the y-axis. And so we have a vertical asymptote. So there's our basic shape of y equals log base 3 of x. So now we'll do the same thing to graph g of x, which is log base 1/3 of x. So once again, if I replace g of x with just y, we have y equals log base 1/3 of x. And then easiest to rewrite this in its exponential form. So starting with the base, we have 1/3 raised to the y power is equal to x. So once again, we'll generate this graph by making a table of values. I'm going to try to fit mine in over here. But looking at the placement of x and y, since y is in the exponent, it is easiest for us to go ahead and choose the exponents. So fill up the y side of your table, and then we'll go ahead and do the computation. So in other words, we're going to have 1/3 raised to the -2 power. 1/3 raised to the -2. So that's basically going to give us the reciprocal of 1/3, which would be 3 over 1, or just 3, and then we'll be squaring that, and 3 squared would be 9. So when y is -2, x is going to be 9. So trying that again, let's input a -1 for our exponent. 1/3 to the -1 power. Again, we'll get the reciprocal of 1/3, which is 3, 3 over 1, raised to the first power, which is going to give us just plain 3. Then we have 1/3 raised to the 0 power. Anything to the 0 power is going to give us 1. 1/3 to the first would be 1/3, and 1/3 squared would be 1/9. So we're just using the exponential form of this function to generate our table, and now we'll plot these points. So when x is 9, we're going right 9, y is -2. So we have the coordinate 9, -2, 3, -1, 1, 0. Those are our three good lattice points, or integer x and y coordinates. And then we have the fractions. So right 1/3, up 1, small point, close to the y-axis, and right 1/9, up 2. You can barely see that one. So we know the basic shape of this curve, because of those fractions, we know that this curve is going to hug the y-axis, and then we have our basic shape for this logarithmic curve. G of x equals log base 1/3 of x. So the purpose of having you graph both of these side by side, several purposes. One is for you to see how it's essential for you to rewrite the function in its exponential form. That's really what's going to help you generate the graph. So when you have a logarithmic function that you're choosing to graph, if you'll take that parent function and rewrite it in exponential form, that's the easiest way to generate a table of values to allow you to plot some points. But I also want you to see some of those common features of all logarithmic graphs. So you'll notice both of these functions have a vertical asymptote. So I'm graphing the vertical asymptote here as a dotted red line. Okay, so they both have a vertical asymptote, and the equation for that vertical asymptote is x is equal to 0. You'll also notice in the table that both of these functions share the point 1, 0. So you see that we have an x-intercept for both of these curves of 1, 0. That's another common feature of all of our logarithmic functions. The x-intercept is going to be 1, 0. And in fact, let's go ahead and write this list down. Why don't I go ahead and switch over here to our common features of all logarithmic functions. F of x equals log base b of x. So first common feature. So we had listed that the logarithmic functions are going to have a vertical asymptote. The equation for that vertical asymptote is going to be the line x equals 0. Another feature, we notice that they're all going to have that common x-intercept, which is the point 1, 0. And let me mention, the order in which we write these features doesn't matter, of course. All right, let's look for another common feature, going back to our graphs. Let's talk about the domain and the range. Hopefully you can see that both of these graphs, both my orange and the green, they have the same domain. The domain is from 0 to infinity. They also have the same range, lowest to highest. The range is from -infinity to +infinity. So we can list that for an additional common feature, that the domain is from 0 to infinity with a parenthesis on 0 because we have that vertical asymptote that we're not going to intersect. And the range is all real numbers. So every basic logarithmic function, the parent function, will have a domain 0 to infinity and a range of all real numbers. And lastly, let's look at whether or not these are increasing or decreasing functions. So hopefully you can see when you take a look again at the basic shape, and I'll kind of highlight this, looking at the first graph, the one I have in orange. As we go from left to right, if I were to trace this graph and highlight it, you'll notice that my y values are getting larger. So this is an increasing graph. And if I look at the green graph from left to right, if I trace it with this highlighter, you'll see my y values are getting smaller. So this is a decreasing graph. And one way to tell whether or not your function is going to be increasing or decreasing is to go back to the original curve and take a look at the base. My function f of x had a base of 3. That's why this parent function is increasing. Whereas my function g of x had a base of 1/3, and that's why my function is decreasing. And this should be familiar to you, very similar to how we looked at exponential functions and whether or not they were going to be exponential growth or decay functions. It all depended on the base. So same idea here. So we know that if my base, which I'm just calling b, if my base is a number greater than 1, then I know that the graph increases. All right, the graph is always increasing. Once again, we're, remember, talking about the parent function. we will have an increasing graph. Y values are going to be getting larger if the base is greater than 1. Whereas in my second example, the base was 1/3. So that's if your base is a fraction between 0 and 1. So we'll write if 0 is less than b is less than 1, that means the base is between 0 and 1, then that tells me that my graph is always decreasing. So for a base, a fractional base between 0 and 1, the y values are going to be getting smaller. They'll be decreasing as opposed to increasing. And those are our basic features of all logarithmic functions.